Welcome to the deep dive. You know, every time we build something in Java, like whether it's a simple little app or some huge enterprise system, we're really standing on the shoulders of some really powerful fundamental concepts. But sometimes it feels like we're just memorizing the what without truly getting the why or, the how. So today, our mission is kind of cut through that noise. We're going to take a set of common Java concepts, the ones that really underpin everything, and actually dig into them. The goal isn't just to, understand the definitions, but to unlock those aha moments, giving you insights you can actually use. We're aiming for real understanding, not just memorization.
That's exactly it. What's really fascinating here is how these concepts, which seem pretty straightforward on the surface, actually reveal the elegant architecture and design philosophy that makes Java so robust.
Yeah.
Getting these right isn't just about, acing an interview. It's about fundamentally improving how you design, build, and debug your systems. It means writing, well, more efficient and resilient code in the long run.
All right, let's unpack this journey. Let's start at the very beginning. How Java handles its most fundamental building block, the object, and specifically how it understands their unique identity. We're talking hash code and equals.
Ah, yes, the classic duo.
Mhm.
Hash code is basically an integer value linked to an object. It's mainly used by hash-based collections, like hash map or hash set. Think of it as a quick initial fingerprint. Its main job is really to speed up retrieval. It gives you a way to quickly narrow down where an object might be stored in, say, a hash map.
Okay, so if hash code is the quick fingerprint, what happens if you just don't have one? Or if it's not very good, like poorly implemented?
Right. Well, if you don't implement hash code at all, or if you implement it badly, those hash-based collections, they become incredibly inefficient. I mean, really slow. Without a reliable way to map an object to a specific bucket using its hash code, the collection often just degrades into a linear search. It basically turns what should be an O1 operation, super fast, into an ON nightmare. Yeah, and comparing objects also gets a lot slower without a good hash code to quickly filter candidates.
This brings us straight to the famous equals and hash code contract. That's a core rule, isn't it?
Oh, absolutely, and violating it.
Yeah.
That leads to some really subtle, hard-debug problems later on. The contract basically says, if two objects are considered equal by the equals method, then their hash code methods must produce the exact same integer result. Always. No exceptions. But, and this is key, the reverse isn't necessarily true. If two objects have the same hash code, they are not guaranteed to be equal. They just happen to land in the same bucket.
Ah, okay.
Yeah, so equals still has to do the final check to see if they're truly the same.
Okay, here's where it gets really interesting and honestly probably a common mistake. What if you implemented a truly terrible hash code? Like, say your hash code method just always returns 1, you'd return 1, that's it.
Oh boy. Yeah, that would be a performance disaster waiting to happen. Imagine you have a hash map or hash set with, say, millions of objects. If every single object's hash code returns 1, every single object would get shoved into the exact same bucket within that hash table's internal array.
So instead of spreading them out nicely across different buckets?
Precisely. Your hash map would essentially just become one giant linked list, or maybe one giant tree since Java 8. But still, everything's crammed together. Every put, every get, every remove operation would require iterating through potentially millions of objects in that single bucket. Your performance degrades from that beautiful near constant time O1 to agonizingly slow ON.
Wow.
It's like trying to find one specific book in a library where every single book has just been tossed into the same massive unsorted pile. The whole point of using a hash-based collection speed is completely undermined.
Right, okay. That makes sense. So moving from object identity, let's shift gears to how we manage an object state. How we save it, restore it, maybe even create copies. Java gives us a few different ways to do this, right?
Indeed. The simplest one is probably serializable. It's what we call a marker interface.
Marker interface, meaning?
Meaning it actually has no methods to implement.
Yeah.
By just putting implement serializable on your class, you're basically just telling the JVM, hey, it's okay, this object state can be converted into a byte stream and later reconstructed. It relies entirely on Java's default serialization process.
Okay, simple enough. And then there's externalizable. What's the difference there? What's the upgrade?
Right, so externalizable actually extends serializable, but it gives you explicit control. Instead of just letting the JVM guess or use defaults, you have to implement two methods, write external and read external. This is really powerful because it lets you decide exactly what data gets written out and how. It can lead to, well, better performance, definitely smaller serialized data. and gives you much more flexibility if you need to handle things like versioning or specific data formats that the default process wouldn't understand.
Gotcha. And then we have clonable. How does that fit into this picture of managing state?
Clonable is another marker interface. It signals that an object can be copied using the object.clone method. But, and here's the really important bit, object.clone performs what's called a shallow copy by default.
Shallow copy. Okay, what does that mean in practice?
It means if your object contains fields that are references to other objects, the clone method copies the references, not the actual objects they point to. So the original object and the cloned object will end up sharing those same reference objects.
Huh?
If you change one of those shared objects through the clone, the original sees the change too, and vice versa.
Ah, that's a crucial distinction. That could lead to some unexpected behavior if you're not careful.
Definitely.
So when would you typically reach for clonable versus, say, serializable?
Generally, you'd use clonable for creating a copy of an object state within the same JVM instance, often for internal manipulation or maybe some temporary state duplication. Serializable, on the other hand, is primarily designed for persistence, saving object's state to disk or sending it across the network, maybe reconstructing it in a completely different JVM instance later on.
That brings up a really important question, especially in today's world of microservices and different systems talking to each other. Can Java's built-in serialization actually communicate with other programming languages? Like, if I serialize something in Java, can my Python service understand it?
That's a great question. And the short answer is a pretty definitive no. Java serialization is very tightly coupled to Java's internal object model, its class structure, the JVM itself. It wasn't designed for cross-language compatibility at all.
Okay, so if I need Java to talk to Python or Go or whatever.
Then you must use language-agnostic formats, things like JSON, which is ubiquitous now, or XML if you need more structure, or maybe binary formats like Google's protocol buffers or Avro if performance and size are critical. These formats are designed specifically for interoperability. You can then send this data over standard protocols like HTTP, WebSockets, gRPC, whatever makes sense for your architecture. They provide that common ground that systems written in different languages can all understand.
Makes sense. All right, switching gears slightly, let's talk about string. Why is string in Java such a special case? Particularly its immutability, the fact that it can't be changed once created.
String immutability. It's not just a minor detail, it's a really fundamental design choice in Java with some massive benefits. First off, security. Think about it. Strings are used everywhere for sensitive data passwords, database URLs, file paths, API keys. If strings were mutable, their values could potentially be altered after creation, maybe accidentally, maybe maliciously, leading to some really serious security vulnerabilities. Imagine passing a file path string to a method and some other thread changes it underneath you before it gets used. Chaos.
Okay, yeah, I can see that. So once a string is created, its value is absolutely set in stone.
Exactly. And this immutability also makes caching much, much simpler and more effective. String literals, strings defined directly in your code like hello, are heavily cached in the Java string pool. This saves a ton of memory because multiple parts of your code can reuse the exact same string object. If strings could change, this whole caching mechanism would become incredibly complex, probably error-prone, and much less effective.
Any other reasons?
Oh yeah. Immutability inherently makes string objects thread-safe. You can safely share string instances between multiple threads without worrying about synchronization or race conditions related to the string's value changing. This simplifies concurrent programming quite a bit. And finally, the JVM itself can perform numerous optimizations, like with the string pool, precisely because it knows that the value of a string object will never ever change after it's created.
This leads perfectly into a common security best practice. Why do we often see advice to use a char, a character array, for sensitive stuff like passwords instead of just using a string?
Right. This is a direct consequence of strings' immutability and how it interacts with memory and the string pool. Because a string is immutable, its underlying character data persists in memory until the garbage collector eventually decides to clean it up. There's no way for you to force it to be wiped sooner. Plus, if it's a literal, it might live on in the string pool for the entire application lifetime. This means a password stored as a string could potentially linger in memory much longer than necessary. It might show up in memory dumps if the application crashes, or maybe even be accessible through tricky reflection techniques.
Okay. And a char avoids this.
Exactly. A char is mutable. As soon as you're done verifying the password, you can explicitly iterate through the array and overwrite each character with a 0 or a space or random garbage, whatever. You can immediately wipe the sensitive data from memory, giving you much finer-grained control over its life cycle. It also won't end up in the string pool. So for things like passwords, char is generally considered the safer choice.
Okay, that's clear. Now let's dive into the fascinating, sometimes tricky world of concurrent programming. How Java helps threads play nicely together, or at least stops them from trampling all over each other. The synchronized keyword seems central here.
That's absolutely right. Synchronized is Java's built-in mechanism for ensuring mutual exclusion, or locking. When a thread enters a synchronized block or method, it has to acquire the intrinsic lock associated with a specific object, for instance methods, or the class itself, for static methods. While that thread holds the lock, only that thread can execute code protected by the same lock. Any other thread trying to enter a synchronized block on the same lock will be blocked until the first thread exits and releases the lock. This is fundamental for preventing multiple threads from simultaneously modifying shared data, which is how you get those nasty race conditions.
Okay, so synchronized handles the locking, but beyond just locking, how do threads actually, communicate? If one thread needs to wait for something another thread is doing, how does that work?
That's where the trio of wait, notify, and notify all comes in. These are the foundational methods for interthread communication in Java. When a thread calls wait on an object, it does two crucial things. First, it pauses its own execution, and second, it releases the lock it currently holds on that object. It then enters a waiting state, essentially joining a queue of threads waiting on that specific object's monitor.
And it just waits there until...
Until another thread calls either notify or notify all on that same object. A call to notify wakes up one single arbitrarily chosen thread from that object's waiting queue. Notify all wakes up all the threads waiting on that object's monitor. Now, being woken up doesn't mean they run immediately. Those awakened threads then have to compete again to reacquire the object's lock before they can actually resume execution from where they left off after the wait call.
I always found it interesting that those three methods, wait, notify, and notify all, are defined in the object class itself. Why there? Why not in the thread class or somewhere else?
That's a very deliberate and quite elegant design choice. In Java's concurrency model, any object can potentially serve as a monitor or a lock for synchronization and communication. By placing wait, notify, and notify all in the object class, it means that every single object instance in Java automatically inherits these capabilities. You don't need special lock objects. Any plain old Java object can be used as the basis for inter-thread coordination. It makes the mechanism incredibly flexible and universally available.
Okay, let's talk about a scenario that sometimes trips people up. Imagine you have a class, and it has both a static synchronized method and a regular instance synchronized method. What are the locking implications if different threads try to access these methods so they interfere? Great question, because the locking behavior is quite different. A static synchronized method acquires a lock on the class object itself, the .class representation of that class in the JVM. This means that only one thread can be executing any static synchronized method of that specific class at any given time across the entire JVM, regardless of how many instances of that class might exist. It's effectively a class-level lock.
Okay, one lock for all static synchronized methods in that class.
Right. An instance synchronized method, on the other hand, acquires a lock on the specific object instance that the method was called on. There's this reference. So multiple threads can execute synchronized instance methods concurrently, but only if they're operating on different instances of the class. If multiple threads try to call synchronized instance methods on the same object instance, only one will get the lock at a time, the others will block.
So it's like the difference between locking the entire factory blueprint versus locking just one specific machine built from that blueprint.
That's a perfect analogy. Class lock versus instance lock. They operate independently. A thread holding the class lock doesn't prevent another thread from acquiring a lock on a specific instance, and vice versa.
Let's quickly touch on a thread's life journey. What are the main states it typically cycles through?
Sure. A thread usually starts in the new state, right after it's created but before start is called. Once start is called, it moves to the runnable state. This means it's ready to run and is just waiting for the thread scheduler to give it some CPU time. When the scheduler picks it, it enters the running state. From there, it can transition to various waiting states like blocked, if it's waiting to acquire a lock, waiting if it called wait, or join, or timed waiting like thread.sleep, or wait with a timeout. Eventually, once its run method completes, either normally or due to an exception, it enters the terminated state.
Got it. And what's a common sort of gotcha for new developers when they're trying to actually kick off a new thread? What happens if you mistakenly call the run method directly on a thread object instead of calling start?
Ah, yes, the classic run versus start confusion. This trips up a lot of people initially. If you call the run method directly, it simply executes the code defined inside the run method, but it does so within the current thread. It's just like calling any other regular method. No new thread is created, no concurrency happens, you basically just run the tasks sequentially.
So no parallelism.
Not at all.
Ammo.
The magic happens when you call the start method. That's the method that actually tells the JVM, okay, create a brand new thread of execution, allocate resources for it, and then within that new thread, invoke the run method. So always remember .start is what actually launches the new thread and achieves concurrency.run. Just executes the task's code in the caller's thread.
Good clarification. Okay, shifting gears again, let's dive into how Java organizes and processes data efficiently. We're talking collections and, of course, the incredibly powerful Stream API. Let's start with a workhorse, hash map. How does it actually work under the hood, and how does it handle those pesky collisions?
Right. HashMap is really a master class in balancing speed and flexibility. Internally, it uses an array, often called a table, which consists of buckets. When you put a key-value pair into the map, Java first takes the key you provide and calculates its hash code. This integer hash code is then internally processed, usually involving some bit shifting and modulo operations, to determine which bucket index in the array that entry should ideally go into.
Okay, so the hash code points to a bucket. But what if two different keys end up having hash codes that point to the same bucket index? That's a collision, right?
Exactly. Collisions are inevitable in hashing. When a collision occurs when multiple key-value pairs need to go into the same bucket, HashMap has to handle it. Historically, before Java 8, each bucket was simply a linked list. If multiple entries hashed to the same bucket, they were just added to the end of that bucket's linked list. However, since Java 8, there's a very clever optimization. If the number of entries in a single bucket's linked list grows too large, specifically, if it exceeds a certain threshold, which defaults to 8, that linked list is automatically converted into a balanced red-black tree.
Whoa, okay, a tree instead of a list. Why the switch? What's the benefit?
It's all about maintaining good performance, even in the face of, well, either poorly designed hash code functions or just unavoidable clustering of hash codes. With a linked list, if you have a lot of collisions in one bucket, searching for an element within that bucket becomes an O-AND operation. You might have to scan through the whole list. It gets slower and slower as more items collide there. A red-black tree, being a self-balancing binary search tree, guarantees O-log-N performance for search, insertion, and deletion operations, even in the worst-case collision scenarios. This switch ensures that HashMap generally maintains its excellent average performance characteristics, usually close to O1, even when collisions get heavy. It makes the map much more resilient to bad hashing.
Okay, that makes sense. And when you retrieve an object using getKey,
When you call get with a key, Java again calculates the key's hash code to quickly figure out the correct bucket index. Once it finds the bucket, it then needs to find the exact entry within that bucket, which might be a list or a tree. It does this by iterating through the entries in that bucket and using the equals method to compare the provided key with the keys stored in the bucket until it finds a match. And this really highlights again why having both a correct hash code and a correct equals implementation that adhere to the contract is absolutely critical for HashMap and HashSet to function correctly and efficiently. One finds the bucket, the other finds the specific item within the bucket.
sticking with collections for a moment, what's the core difference between choosing a hash set versus a tree set? When would you use one over the other?
The fundamental difference really boils down to ordering and the underlying implementation, which impacts performance. A hash set makes absolutely no guarantee about the order in which elements are stored or retrieved. It's optimized purely for speed-fast additions, removals, and checking for containment. On average, these operations are O1, constant time. Internally, as the name suggests, it's actually backed by a hash map where the values are just a dummy placeholder. A tree set, conversely, maintains its elements in a sorted order. This order is either the element's natural ordering, if the elements implement the comparable interface, or a custom ordering defined by a comparator that you provide when you create the tree set. Because it needs to maintain this sorted order, it's internally backed by a tree map, which uses a red-black tree. This means its operations add, remove, contains typically have a time complexity of O log n, which is slightly slower than hash sets O1, but still very efficient.
So use hash set for speed when order doesn't matter, tree set when you need elements automatically sorted.
Exactly. Speed versus order. That's the main trade-off.
This naturally leads us to comparable versus comparator. You mentioned them with tree set. How do you decide which one to use for defining object ordering?
Right. Comparable is used to define a single natural ordering for objects of a particular class. The class itself implements the comparable interface and provides the logic within its comparative method.
Yeah.
You'd use this when there's one obvious primary way to sort objects of that type, like sorting strings alphabetically or integers numerically or maybe dates chronologically. It becomes the default order for that class. Comparator, on the other hand, is used to define custom or multiple different orderings. It's typically implemented as a separate class, or often nowadays as a Lambda expression. This is incredibly flexible because it allows you to define various sorting strategies for the same object type without modifying the original class itself. For instance, you could have a list of employee objects and sort them by name using one comparator, then sort the same list by salary using a different comparator, and then maybe by hire date using yet another one. Comparator gives you that externalized, pluggable sorting logic.
Got it. Okay, now for something I think really changed the game in modern Java, the Streams API, introduced back in Java 8. It was a huge shift for how we process data collections, wasn't it?
Oh, absolutely. The Streams API was, and still is, a game changer. It provides this really powerful, functional style approach to processing sequences of elements. It's important to remember, a stream itself isn't a data structure. It doesn't store elements. It's more like a pipeline or a conveyor belt for processing data from a source, like a collection, an array, or even an I/O channel. The advantages are huge. It often leads to incredibly concise and much more readable code compared to traditional imperative loops. It makes parallel processing surprisingly straightforward. You can often just swap .stream for .parallelstream and let the framework handle the complexities of parallel execution. And critically, it embraces lazy evaluation.
Lazy evaluation, you mentioned that. Why is that such a big deal? Can you elaborate on why that's so powerful for performance?
Definitely. Think about how you might process data traditionally. If you have a list and you want to filter it, then map it, then find the first element that matches, you might iterate multiple times or create intermediate collections. With streams, lazy evaluation means that the intermediate operations, things like filter, map, sorted, distinct, don't actually do any work immediately when you call them. Instead, they just build up a description of the processing pipeline. The actual processing only kicks off when a terminal operation is called, something like for each collect, reduce, find first, or count. This allows for some amazing optimizations. For example, imagine you have a massive stream of data, you apply a filter, then a map, and then you call find first. Because it's lazy, the stream might only process elements one by one through the filter and map stages, just until it finds the first element that satisfies the condition. It doesn't need to process the entire rest of the potentially huge stream. It only does the minimum work necessary to produce the result requested by the terminal operation. This can lead to significant performance gains, especially with large data sets or expensive operations.
That makes perfect sense. It avoids so much unnecessary work. So let's take a practical example. If I'm trying to solve a common coding challenge, like finding the first non-repeated character in a given string using streams, how could I approach that cleverly, maybe keeping that lazy idea or efficient processing in mind?
That's a great challenge that really showcases the power and sometimes the subtleties of streams. Here's how you could approach it. First, you'd get the stream of characters from the string, probably using string.chars. .map2 of JC is charc. Then the core idea is to count the frequency of each character. You can do this using collectors.groupingby. However, you need the first non-repeated character, which implies order matters. Standard hash map doesn't guarantee order. So the trick is to use a linked hash map as the map implementation for grouping by, because linked hash map remembers the insertion order. So you'd collect into a linked hash map character, long using collectors.groupingby, CCC, linked hashmap.new, collectors.counting. This gives you a map where keys are characters in their original appearance order and values are their counts.
Okay, so now I have the counts in order.
Exactly. Now you stream the entries of this map, map.entryset.stream. You then filter this stream to keep only those entries where the value is exactly 1L. Since the link hash map preserved the original order, the first entry that passes this filter will correspond to the first non-repeated character in the original string. So you just call find first on this filtered stream of entries. If find first returns an optional containing an entry, you just get the key, the character, from that entry. If it returns an empty optional, it means there were no non-repeated characters. It's a really elegant solution combining frequency counting, order preservation, and stream processing.
Wow, that's neat. Using linked hash map in the collector is the key insight there for preserving order.
Precisely.
Okay, let's quickly touch on optional. It also arrived with Java 8. Why was that introduced? What problem does it solve?
Optional was introduced primarily to provide a better, more explicit way to handle the potential absence of a value, aiming to reduce the prevalence of the dreaded null pointer exception. Before optional, methods that might not find a result would often just return null. The caller then had to remember to check for null, and forgetting to do so would lead to NPEs at runtime. Optional T is essentially a container object that may or may not contain a non-null value of type T. Instead of returning null, a method can return an optional.empty if no value is found, or optional.f value if a value is present. The key benefit is that the type system now forces the caller to think about the absence case. You can't directly get the value out without explicitly handling the possibility that it might be absent, using methods like isPresent, isEmpty if present consumer, or else default value, or else getSupplier, or else throw. It makes code more robust and self-documenting about nullability.
Got it. Helps avoid those nasty runtime surprises. Now, thinking about robustness in concurrent situations again, we often hear debates about using concurrent hash map versus just wrapping a regular hash map with collections.synchronized map. What's the real-world performance difference, especially when things get busy under heavy concurrent load?
Yeah, this is a huge one for performance in multi-threaded applications. Using collections.synchronized map basically takes your standard hash map and wraps every single one of its methods, put, get, remove, size, everything inside a synchronized block that locks on the map object itself. This means only one thread can access the map at any given time for any operation. It creates a single point of contention. It's like having only one cashier lane open in a massive supermarket during peak hours. Throughput grinds to a halt because everyone has to wait in the same line. This becomes a massive bottleneck under even moderate concurrency.
Okay, so synchronized map is simple but slow under load. How does concurrent hash map solve that bottleneck problem?
Concurrent hash map is much more sophisticated. Instead of one single lock for the entire map, it uses a technique often referred to as lock striping or segmenting, though the exact internal implementation has evolved across Java versions. The basic idea is to divide the map's internal hash table into multiple independent segments or partitions. Each segment has its own lock. When a thread needs to perform an update operation, like put or remove, it only needs to acquire the lock for the specific segment where the key resides. Other threads can simultaneously acquire locks and operate on different segments concurrently. It's like opening multiple checkout lanes in our supermarket analogy. This dramatically increases the level of concurrency and throughput, especially for write operations. Even better, for many read operations, like get, concurrent hash map is often designed to work without requiring any locking at all, leveraging volatile reads and careful memory visibility techniques. This makes reads incredibly fast, even under high write contention. So for almost any scenario involving shared mutable map state accessed by multiple threads, concurrent hash map is vastly superior in terms of performance and scalability compared to a synchronized map.
That's a really clear explanation. The lock striping makes all the difference. All right, let's zoom out again, maybe look at some of Java's deeper architectural foundations and how the language itself has evolved. We have to start with class loaders. They sound fundamental, but what exactly are they and why are they so important to how Java works?
Class loaders are absolutely fundamental. They are a core part of the Java runtime environment, JRE, and the Java Virtual Machine, JVM. Their primary job is to dynamically load Java class files, the .class files containing bytecode, from the file system, network, or other sources into the JVM's memory as they are needed by the application. They take that bytecode, verify it for security and correctness, and then convert it into an internal representation, usually a class object, that the JVM can actually execute. They are essentially what enables Java's famous write once, run anywhere promise, because they abstract away the underlying file system and loading mechanisms.
Okay, and I know there isn't just one class loader. There's this hierarchy, right? The bootstrap, platform extension, system application loaders. Why the complexity? Why not just have one central loader for everything?
That hierarchy, and the delegation model it follows, is crucial for several reasons: flexibility, security, and preventing namespace collisions you typically have. 1. Bootstrap class loader loads the core Java APIs like java.lang, .object, string, etc. It's usually implemented in native code, C++, and is the parent of all other loaders. 2. Platform class loader, formerly extension, loads classes from the JDK's extension directories, providing a standard way to add functionality beyond the core Java SE platform. 3. System application class loader loads the classes from your application's class path and directories and JAR files you specify when you run your application. The delegation model works like this. When a class needs to be loaded, the request first goes to the application class loader. It delegates the request up to its parent, the platform loader. The platform loader delegates up to the bootstrap loader. The bootstrap loader tries to load the class first. If it finds it, for example, java.lang string, it loads it and the process stops. If it doesn't find it, the request comes back down to the platform loader, which tries to load it from its locations. If it still can't find it, the request comes back down to the application loader, which then finally tries to load it from the application's class path.
So it always asks the parent first. Why?
This parent-first delegation prevents chaos. It ensures that core Java classes are always loaded by the bootstrap loader, preventing an application from accidentally or maliciously replacing a fundamental class like java.lang object with its own version. It creates isolated namespaces. Classes loaded by a child loader can see classes loaded by its parent, but not necessarily vice versa, unless explicitly managed. This is vital for security, sandboxing, for avoiding conflicts between different libraries that might use the same class names, and for enabling complex scenarios like application servers running multiple independent applications, each with potentially different versions of the same library, loaded by different class loaders. Having multiple loaders provides essential modularity and isolation.
That makes a lot of sense. Java itself has evolved so much over the years, too. Looking back at some major long-term support LTS releases, what were some of the real standout, impactful features that came with, say, Java 8, Java 11, and the more recent Java 17?
Oh yeah, the evolution has been significant. Java 8 was arguably the biggest revolution since Java 5. It brought Lambda expressions, functional interfaces, and, as we discussed, the incredible Stream API. These completely changed the way we write idiomatic Java code, embracing functional programming paradigms. It also gave us optional to combat NPEs, the much-needed new date and time API, java.time, default methods and interfaces, and method references. It was a massive leap forward. Java 11, the next LTS release after 8, built on this. Key features included var for local variable type inference, which could now also be used in Lambda parameters. Several useful new methods added to the string class, like as plank, lines, and strip. The standardization of the built-in HTTP client API, making it easier to make HTTP calls without external libraries. And the ability to run single-file Java source code directly without explicit compilation. It also included experimental versions of new garbage collectors like ZGC.
So more refinement and some key additions. And Java 17, the subsequent LTS, what were the highlights there?
Java 17 brought some really important features into the mainstream. A big one was sealed classes and interfaces, which give you fine-grained control over which other classes or interfaces are permitted to extend or implement them. This greatly enhances modeling capabilities, especially for things like algebraic data types, and improves overall system integrity. It also finalized pattern matching for switch expressions and statements, making complex conditional logic much more concise and less error-prone compared to long chains of if-else-if with instance of checks. And significantly, it marked the Z garbage collector, ZGC, and the Shenandoah GC as production-ready, offering scalable, low pause time garbage collection options, which is huge for applications with large heaps or strict latency requirements.
Sealed classes and pattern matching sound like they really improve code clarity. Okay, moving to something a bit more conceptual, let's quickly revisit the core object-oriented programming OOP principles. We always hear about abstraction, encapsulation, inheritance, and polymorphism. Can you give us a quick practical refresher on polymorphism, particularly the different types we encounter in Java?
Sure. Polymorphism literally means many forms. And in OOP, it's the ability of an object to take on many forms. It's arguably the most powerful OOP principle, enabling flexibility and extensibility. In Java, we primarily see two types. One, compile-time polymorphism or static polymorphism. This is achieved through method overloading. You have multiple methods within the same class that share the same name but have different parameter lists, different number of parameters, different types of parameters, or both. The compiler determines exactly which overloaded method to call at compile time based on the arguments you provide in the method call.
Okay, decided at compile time based on the method signature. And the other type?
2. Runtime polymorphism, or dynamic polymorphism. This is achieved through method overriding. Here, a subclass provides a specific implementation for a method that is already defined in its superclass. The key is that the method in the subclass must have the exact same name, return type, or a covariant return type, and parameter list as the method in the superclass. This allows you to work with objects through their superclass type, but still get the behavior defined in the specific subclass at runtime. For example, you can have an array of animal references, where some elements point to dog objects and others to cat objects. When you loop through the array and call animal.makeSound, The JVM determines at runtime whether to execute the dog's make sound or the cat's make sound, based on the actual object type. This is incredibly powerful for writing generic code that can work with different specific implementations.
And this relates to upcasting and downcasting?
Exactly. Upcasting, animal, is galeen dog, is implicit and safe, treating a subclass object as its superclass type. Downcasting, dog, animal, requires an explicit cast and can fail at runtime if the object isn't actually of the target subclass type, leading to a class cast exception, so you usually check with instance of first. Oh, and a crucial point often missed. Runtime polymorphism applies only to instance methods. Instance variables, fields, do not participate in polymorphism. They are accessed based on the reference type, not the actual object type. Also, static methods cannot be overridden in the polymorphic sense. They are hidden, not overridden.
That's a very important distinction about instance variables and static methods. Thanks. Okay, let's touch on reflection. It feels a bit like Java looking in a mirror at runtime. It allows you to inspect and even manipulate things dynamically. What is it really, and where do we actually see it used in practice?
Reflection is indeed a powerful, almost metaprogramming capability in Java. It allows a running Java program to examine or introspect itself and manipulate internal properties of the application at runtime. You can inspect classes, interfaces, fields, and methods at runtime without knowing their names at compile time. Key components are classes like java.lang.class, java.lang.reflect.method, field, and constructor. You can use these to find out about a class's members, including private ones, and even invoke methods or change field values dynamically.
So why would you need to do that? It sounds potentially dangerous.
It can be dangerous if misused, as it bypasses compile time type checking and can break encapsulation. However, it's absolutely essential for many frameworks and tools. Think about dependency injection frameworks, like Spring. Spring uses reflection heavily to scan your classes for annotations, like an auto-wire to component, figure out dependencies, dynamically create bean instances, class.forName, .get declared constructor.new instance, and inject dependencies into private fields, all without you writing explicit wiring code. Object Relational Mapping, ORM, frameworks, like Hibernate. Hibernate uses reflection to inspect your entity classes, figure out the mapping between fields and database columns, and dynamically populate object fields with data retrieved from the database or read field values to generate SQL statements. Testing frameworks like Junit. Junit uses reflection to discover methods annotated with @test, @beforeeach, etc., and invoke them dynamically. It also uses it for things like accessing private fields or methods if needed for certain test scenarios. Serialization libraries. Many libraries that convert Java objects to formats like JSON or XML use reflection to discover the fields of an object and read their values. So while you might not use reflection directly in your everyday application code very often, it's the invisible engine powering many of the frameworks that make Java development productive. It enables that powerful decoupling and convention over configuration approach.
That makes a lot of sense. It's the magic behind the curtain for many frameworks. Okay, let's shift gears now into the realm of design patterns. These are like the reusable blueprints, the well-tested solutions to common software design problems we encounter again and again. They're not about specific algorithms, but more about how you structure your code for things like flexibility, robustness, and maintainability. Let's start with a really famous one, maybe infamous sometimes, the singleton pattern.
Ah, the singleton.
Yeah.
Yes, it's probably one of the best-known creational patterns. Its core intent is pretty simple. Ensure that a class has only one instance and provide a single global point of access to that instance. You often see it proposed for things where you logically only need one of something in the entire system, maybe a configuration manager, a logging service, a connection pool manager, though even that can be debated, or perhaps a hardware interface proxy.
Sounds straightforward enough, but I've heard it called an anti-pattern by some, and that it can be tricky to get right. Where do developers most often stumble with singletons, and what are some of the maybe less obvious consequences?
You're absolutely right. It's deceptively simple on the surface, and its overuse, especially in modern architectures that favor dependency injection, is often frowned upon. Common pitfalls include 1. Thread safety. If you implement lazy initialization, creating the instance only when it's first requested, without proper synchronization, multiple threads could potentially race to create the instance, resulting in multiple instances and violating the core principle. You need techniques like synchronized methods or, preferably, double-checked locking with volatile to do lazy initialization safely. Eager initialization, creating the instance when the class is loaded, is simpler and inherently thread safe. 2. Serialization. This is a sneaky one. If your singleton class implements serializable, simply deserializing it will typically create a new instance every time, again breaking the singleton guarantee.
Oh, wow. How do you fix that?
The standard solution is to implement the read-resolve method within your singleton class. This special method is invoked during deserialization, and you implement it to return the existing singleton instance. For example, return instance. This effectively intercepts the deserialization process and ensures only the canonical instance is ever returned. 3. Cloning. If your singleton class happens to inherit clonable, maybe from a superclass, or implements it directly, someone could potentially call clone on the instance and create a copy. To prevent this, you should override the clone method and either return the existing instance or, more commonly, throw a clone not supported exception. But beyond these implementation details, the biggest architectural drawback of singletons is that they introduce global state and tight coupling. Because they provide a global access point, any part of your code can potentially grab the instance and interact with it, making dependencies implicit and hard to track. This makes unit testing much harder. How do you mock a global singleton easily? Makes the code harder to reason about and can violate principles like dependency inversion. That's why dependency injection is generally preferred today for managing shared components.
That's a really thorough breakdown of the singleton's challenges. Okay, let's look at another creational pattern, one that helps with complex object construction, the builder pattern. What problem does it specifically solve, and how does it lead to cleaner code compared to, say, just using constructors?
The builder pattern is fantastic for constructing complex objects, especially objects that have a large number of fields, many of which might be optional, or where the construction process itself is intricate. Its primary goal is to separate the construction of a complex object from its representation.
So, like, if you have a class, maybe user configuration with, like, 15 different settings, and maybe only 3 are required and the rest are optional.
Exactly. That's the perfect scenario for a builder. Without it, you often end up with what's grimly called the telescoping constructor anti-pattern. You'd have one constructor with the 3 required fields, another with 3 required plus 1 optional, another with 3 required plus a different optional, another with 3 required plus 2 optionals. It explodes combinatorially. It becomes incredibly messy, hard to read, and very error-prone. It's easy to mix up the order of Boolean or integer parameters, for instance. With a builder pattern, you typically create a separate, often static nested builder class inside your main class, userconfiguration.builder. This builder class has methods for setting each of the properties, e.g. builder.setAmirZone UTC.setNotificationsEnabled to true.setThemeDark. These setter methods usually return the builder instance itself, allowing for fluent chaining of calls. Finally, the builder class has a build method that actually creates and returns the immutable user configuration object, often validating the state in the process. Think of Java's own string builder you append multiple times and then finally call to string to get the result, or stream.builder. This approach makes the code highly readable. It reads like a configuration script, eliminates the need for numerous constructors, makes it easy to enforce invariants. Required fields can be checked in the build method, and allows the main object, user configuration in this case, to be immutable once constructed.
That sounds much cleaner. Are there any downsides?
The main disadvantage, if you can call it that, is that it does involve writing a bit more boilerplate code initially, because the builder class often needs to mirror the fields of the class it's building. But the improvement in clarity, safety, and maintainability for complex objects usually far outweighs this initial effort.
Okay, that makes sense. Let's shift now to behavioral patterns. These are all about how objects interact and how responsibilities are distributed among them. One I find particularly elegant, especially for decoupling, is the chain of responsibility pattern. Can you maybe illustrate its power with a good real-world analogy or example?
Absolutely. The chain of responsibility pattern is designed to avoid coupling the sender of a request directly to its receiver. Instead, it gives multiple objects a chance to handle the request by passing along a chain of potential handlers. Each handler in the chain decides either to process the request or to pass it along to the next handler in the chain.
So the sender doesn't necessarily know which object will ultimately handle it?
Yeah. Exactly. The sender just initiates the request to the first object in the chain. Think of an ATM withdrawal system. Suppose you request to withdraw $370. The request might first go to a handler responsible for dispensing $100 bills. It checks if it can handle part of the request. It dispenses 3 $100 bills, $300 total, and determines that $70 remains. It then passes the remaining request, $70, to the next handler in the chain, maybe the $50 bill handler. The $50 handler dispenses one $50 bill, sees $20 remaining, and passes that to the $20 bill handler. The $20 handler dispenses one $20 bill, sees $0 remaining, and the process stops. Each handler only knows about the next handler in the chain. It tries to process what it can and passes the rest along. This makes the system incredibly flexible. You can easily add new handlers, like a $10 bill handler, remove handlers, or reorder the chain without modifying the existing handler code or the client code that initiated the request. Other common examples include event propagation in GUI systems or hierarchical logging frameworks where a log message might pass through debug, info, warning, and error level handlers until one decides to log it or passes it on.
That's a fantastic, clear example. Building on this theme of object interaction, what about the observer pattern? This one feels really central to how many modern systems, especially reactive ones, notify different components when something changes.
Yes, the observer pattern is fundamental for building systems where state changes in one object need to trigger actions in other dependent objects without tightly coupling them. It defines a one-to-many dependency relationship. You have one object, often called the subject or observable, which maintains a list of its dependents called observers. When the subject state changes in a way that observers might care about, it automatically notifies all its registered observers, usually by calling a specific update method on each observer.
So classic example, if I go to an e-commerce site and click notify me when a product is out of stock.
That's a perfect real-world analogy. The product is the subject. You and potentially many other customers are the observers who have registered interest. When the product stock level changes, the subject state changes. The system iterates through its list of observers, the customers who signed up, and sends out that notification email or message, calling the update method conceptually. Other classic examples include spreadsheet applications where changing a value in one cell, the subject automatically updates other cells that depend on it, the observers, or weather monitoring systems where a central weather station, subject, broadcasts updates to various display panels or applications, observers. The key benefit is loose coupling. The subject only knows its observers through a common interface, for Ansel observer, and the observers don't need to know the specifics of the subject, only how to react to its notifications. This makes systems much more modular, maintainable, and easier to extend. You can add new observers without changing the subject at all.
Excellent. All right, let's maybe wrap up our patterns discussion by looking briefly at structural patterns. These are more about how classes and objects can be composed to form larger, more flexible structures. The proxy pattern seems quite common. What's its main purpose?
The proxy pattern provides a surrogate or placeholder for another object, essentially to control access to it. Think of it like a middleman or an agent acting on behalf of the real object, often called the subject or real subject. The client interacts with the proxy object as if it were the real object, because the proxy usually implements the same interface, but the proxy intercepts the calls.
Okay, so why would you want this middleman? What kinds of control does it provide?
There are many reasons to use a proxy. Some common scenarios include access control, protection proxy. The proxy can check if the client has the necessary permissions before forwarding the request to the real sensitive object. Lazy initialization, virtual proxy. The proxy can delay the creation and initialization of a resource-intensive real object until it's actually needed for the first time. The proxy holds the place, and only when a method is called does it create the real object. Remote proxy represents an object that lives in a different address space, like on a remote server. The proxy handles the network communication details, making it seem like the client is interacting with a local object. Think RMI or gRPC stubs. Logging proxy. The proxy can log method calls and their arguments before or after forwarding the call to the real object, adding tracing or auditing capabilities non-invasively. Caching proxy. The proxy can cache the results of expensive operations performed by the real object and return the cached result for subsequent identical requests, improving performance. In all these cases, the proxy adds some behavior or control logic without modifying the original real subject class, adhering to the open-close principle. It adds a layer of indirection that provides flexibility.
That makes sense. Adding behavior without changing the original code is always good. Okay, as we transition away from specific patterns, let's tackle one more core Java concept that often causes confusion, especially when dealing with copying objects or ensuring immutability. The difference between a shallow copy and a deep copy. What's the critical distinction there, and why does it matter so much in practice?
This distinction is absolutely fundamental, and misunderstanding it can lead to some really subtle and frustrating bugs, especially when you have objects containing references to other mutable objects. A shallow copy of an object creates a new object instance, and then copies the values of the fields from the original object to the new object. If a field contains a primitive type, like int, float, boolean, its value is simply copied. However, and this is the crucial part, if a field contains a reference to another object, like an address object inside an employee object, a shallow copy copies only the reference itself, not the object it points to. This means both the original object and its shallow copy end up holding references that point to the exact same underlying object.
So if I have employee 1 and create employee 2 using a shallow copy and both have an address field, changing the street in employee 2's address would also change it for employee 1.
Exactly, because they are both referencing the same single address object in memory. Modifying that shared address object through either employee 1 or employee 2 affects what the other sees. This is often not what you intend and can violate assumptions about object independence or mutability. A deep copy, on the other hand, also creates a new object instance, but it goes further. It not only copies primitive fields, but also recursively creates new copies of any objects referenced by the original object's fields. And if those referenced objects themselves contain references, it copies those too, all the way down the object graph. The result is that the original object and its deep copy are completely independent. They, and all the objects they contain transitively, are distinct copies in memory. Changes made to the deep copy or to any object nested within it will have absolutely no effect on the original object or its nested objects.
So deep copy gives you true isolation. When is this most important?
It's critical whenever you need to ensure that modifications to a copied object do not affect the original, or vice versa. This is especially important when 1. Implementing the prototype pattern correctly if the prototype contains mutable referenced objects. 2. Creating truly immutable objects that contain references to mutable types. For example, if you have an immutable order class that holds a list or item, the constructor needs to make a deep copy of the incoming list, and any getter method that returns the list must return a deep copy, or an immutable view, to prevent external code from modifying the order's internal state. Implementing deep copy correctly can sometimes be complex, especially with circular references, but it's essential for maintaining object integrity and immutability guarantees in many scenarios. Java's default object.clone typically performs a shallow copy, so you often need to override it or use other strategies, like serialization, deserialization, or copy constructors, to achieve a deep copy when necessary.
Wow, okay. We've covered a truly staggering amount of ground today. We've gone from the absolute fundamentals of object identity with hash code and equals, through the intricacies of concurrency and locking, explored the power and elegance of the Streams API, and delved into the blueprints of software design with various patterns right up to crucial concepts like deep versus shallow copy. It feels like we've really unpacked the bedrock of Java.
It's been quite a journey, and I think connecting these dots is so important. If you really understand these fundamentals, it connects directly to the bigger picture. It isn't just about, getting through a technical interview, although that helps.
Yeah.
It's genuinely about writing code that is more efficient, much more resilient to errors, and significantly easier to maintain and evolve over time. Having a solid grasp of these concepts really equips you to think critically about the systems you're building or working on. You can diagnose problems more effectively, make better design choices, and ultimately build more robust, scalable solutions that actually stand the test of time and changing requirements.
So as you, the listener, think about all this, what does it all mean for your next project? Or maybe that tricky bug you're trying to solve, or the next system you architect? And here's something to really chew on. Consider how these foundational principles, object identity, memory management, concurrency models, data structures principles developed over decades for classical computing are now being stretched, challenged, and maybe even reimagined with the explosive rise of AI, massive distributed systems, and even the dawn of quantum computing. Do these core Java concepts remain universally true in these new paradigms? Or are we actually on the cusp of needing an even deeper deep dive, a fundamental rethinking of how software itself works?